what I want to do is to go through this Cisco presentation of OSPF characteristics, because the quote experts, unquote, the CCIEs, the book writers say, that have taken the test, say that there's a lot of emphasis on OSPF in the current certification when we do that. So OSPF characteristics 8.1 would be, this would be probably for the Cisco Academy when we do these things. The evolution here, it's a link state routing protocol. We know that. Link state, state of the links. And we have the two versions, up here at the right here, the two versions. We have OSPF v2 for IPv4 and OSPF v3 for IPv6. And when do we have it? It's been around a long time. It's not a brand new protocol. Down here at the bottom, 1988 development work begins. And I think in the presentation that we did last week, we had V1 was developed. We had a version 1, but it was never actually put into production, put into use. Okay, not a problem. Got it. No problem, Justin. And I will do these things. Anyhow, back to this. And when I get distracted when I see the chats, sorry. Anyhow, version 1, there was one, but it was never put into production. Version 2, introduced in 1991. So this is not a brand new protocol that we're talking about when we do that. 98, OSPF v2 was updated in 99, version 3 for IPv6. So it's a pretty well developed protocol when we do this. Link state protocol, state of the links. And up here at the top, interior gateway protocols, we have IPv4, RIP-v2, EIGRP, OSPF, ISIS, BGP. BGP is the exterior gateway protocol that we use. The interiors that are a concern of the enterprise are RIP, EIGRP, OSPF. ISIS is there, and when we get into automation, he'll mention a little bit about ISIS in certain aspects, or actually if you read the Lamley book in the automation, he'll talk about that. RIP next generation for IPv6, which they said they weren't going to do RIP for IPv6, but they did when we do that. EIGRP, OSPF, we kind of looked at those things, but focus right now on OSPF because that is the protocol for the current, the features, and we do the others. There's more to doing these things, to doing the the learning process than just cert test will get you an interview. Cert test is not going to keep you employed. Certifications, and my example for there is we had a guy, and I may have told this story a long time ago. This was there in the NT4 the MCSE. He had memorized questions to do that. He said, and he had a job, and the guy gave him times to study, paid for his tests, paid for his test banks, and all that other good stuff. He said, I got that MCSE, I got certified, and then he expected me to be able to fix stuff. So the certification will get you an interview. The certification will not keep the job for you. Throat again, I don't know what it is. First thing in the morning, I guess, when we do these things. But the features of OSPF. Version 2 supports MD5 and SHA authentication. Version 3, the IPv6, was IPsec for authentication. And we've always said, or you've heard, I'm sure you've heard, that IPv6 is a more secure protocol. IPv6 is a more secure protocol. We can use IPsec in IPv4, but it has to be ported over, and it is a inherent or part of the IPv6 configuration. And over on the right, routing changes trigger updates. So some of the features here, it's classless, efficient, fast convergence, scalable. All of those are characteristics that we really want in all of our protocols. In the bottom right, the administrative distance, which I think we probably have finally maybe beaten into submission, 110, which is kind of in the middle there. Some things that we're not really all that concerned with. BGP is an external protocol, not really a concern of the enterprise. IGRP, we don't have anymore. It's not going to be on any of the routers that you're going to see. RIP, yeah, you probably will see it. EIGRP, internal EIGRP here is 90, so where does it fall in the administrative distance? And the lowest administrative distance, if we have more than one routing protocol running configured on a device, that's going to happen. That's when the administrative distance is going to take over. And then we're going to go into the longest prefix and all the other things that we talked about in order for the router to determine which route it's going to use. Uses the Dijkstra shortest path first algorithm to choose the path, and the routers share the information. The routers each build their own topology table, and the router then calculates its own best path or shortest path from to network to network. Lowest administrative distance is the one added to the routing table. And the administrative distance, again, only comes into play if we have multiple routing protocols configured on a device. The other routes will be there. They'll be, in the background, but the best administrative distance will be the one that gets put into the route table. So we have that administrative distance used to determine the route. The OSPF networks, and we looked at some of these point-to-point, one-to-one. When we did that, we did not have the DR and the BDR. The broadcast multi-access, we have multiples of these things connected to a switch. So we're going to have a broadcast area that we're going to use here. So it's going to be a broadcast multi-access. Multi-access because we have multiples of these things, these OSPF devices. Multiples of these devices here all connected to a switch. So we're going to have a broadcast in here. And when we have these, we're going to have a DR and a BDR. So that, whoever is the DR gets the updates, and then the DR tells all the other users, and we use a multicast. Non-broadcast multi-access is similar to this, except we don't have a broadcast. We have the different devices and the cloud here. What we would have is the hub and spoke. So I'm always trying to draw, but these guys are all going to be connected together. We're in a WAN here when we do these things. So a non-broadcast multi-access, they're all connected, but they're connected together from the cloud. These here are going to be on the same IP network. So that's why it's a multi-access, non-broadcast, NBMA, non-broadcast multi-access. And then we have the point-to-point through the cloud when we have those things. This note here, virtual links. Remember that, and if you look real close, you could probably see this. We have an area 0 here, an area 1 here, and an area 51 back here. So the rule is, if you have more than one area, you got to be connected to area 0. Well, that's not the case back here for area 51. So what we do is it says a virtual link. What you do is create a tunnel through area 1 so that area 51 is now directly connected to area 0. So a couple of things, maybe different concepts, hopefully re-emphasis of some of the things that we talked about with OS. And it won't hurt. Go back, labs, configure. You can do that, packet tracer, build your own. The components of OSPF, the adjacencies, and then the table. The adjacencies are the directly connected folks here. The adjacency, they're going to go in the neighbor table, show IP OSPF neighbor. List the neighbors that the router has established a bi-directional communication with. And you'll get notifications, and I think you probably saw that when I started some of those up, that says that an adjacency was formed. If an adjacency doesn't form, we got to look at the timers to be sure that they match. So the adjacency, the description unique for each router, view them by using the show IP OSPF neighbor. Unique for each router because it can be connected to different devices, obviously. The link state database is the topology table, and it lists the information about all the routers. What's it going to cost us to get there? Remember, OSPF is going to use cost. Represents the network topology, contains the same link state database as all the other routers in the same area. This is what OSPF does. All of the routers get all of the information. Once they've shared all that information one to the other, they all have the same topology table. So they all have the same view of each of them is then in the forwarding list the routes generated by the SPF algorithm, the shortest path, first algorithm. Each of them is then now going to calculate its own best path for each of the networks that are in the topology table. And we can use the show IP OSPF database. We looked at that. The OSPF one doesn't make a whole lot of sense to me, I'll be honest with you. I couldn't go in and say, okay, this is that and this and whatever else. You can look at it and get a sense of what's going on, where it came from, what the costs are. They're all there. But when the topology table gets put together and the algorithm gets run, the Dijkstra algorithm, we come up with a forwarding table, the routing table, the forwarding database. The routing table is going to be there. All the routes generated by the shortest path first algorithm, the Dijkstra algorithm. And it's going to be unique to each router, because even though each of them has the same topology, it's kind of like if you had Google Maps and you're in the same city, but you're in different parts of the city, your shortest path to get to downtown or to get to someplace is going to be different than somebody that's in a different part of the city. Same concept. And a little insert at the top, a little purple insert at the top, hello packets, database description packets, link state request packets, link state update packets, link state acknowledgement packets. The link state announcements that are used, we looked at those a little bit. Yeah, we have them. They are all there, and that's what this system uses, or this topology, this protocol uses in order to share the information. So when we're getting ready to do this, the OS, open shortest path first, the operation one, hello packets, to establish neighbor adjacencies. The hello packets, and these things, these hello packets are get sent out, and I think it was whatever 10 seconds, and 40 seconds was 44 times the hello time was the dead timer for these. The hello packets, if somebody answers, then they're going to be speaking OSPF, and then we can use that hello packet to find neighbors that are using the same protocol. It uses the link state announcements to flood the area with the cost and the state of the links. So what we're now going to do after the hello messages, the adjacencies established, each of them is going to send everything that it knows about to its neighbors. And the neighbors are going to share and to share and to share and to share until eventually everybody's going to have the same information about everything else. There was an old commercial years ago, was for hairspray. If you tell a friend who tells a friend who tells a friend who tells a friend, then eventually everybody's going to know about it. Same kind of concept here. Each router tells every other router, tells a friend who tells a friend, tells a router, tells a neighbor, tells an adjacency who tells an adjacency who tells an adjacency. Then pretty soon everybody's going to have all the same information. Everybody's going to know about everything. And that's what we're looking for here, the topology, so that all of the devices in the network have the same information, the same topology. Each router then builds a topology table from the information that it gets. And then each router runs the SPF, the shortest path first algorithm, resulting in an SPF tree. So the tree is going to be the routing tables that we're going to have. And then after that, each router builds a routing table that includes the path to get to the distant network and the cost to get there. And again, these guys use cost. And if you set them up and look at them, you can, look at the what are the different costs. And I didn't get that table that we would have to go from one to the other. Let me see if I can get one here real quick. Stick it on here just for a second. So the cost for these things, fast Ethernet or faster, 100 meg. This is an old one. Probably now we're going to go to get this one out and put this other one in. So this one, the 10 gig, the gig actually is fast Ethernet 100 meg. So they're going to be a cost of one. Ethernet 10 meg, serial 64. And if you think back to some of the ones that we saw that we were looking at in the demo, we had the 64s, the 65, the 66 sort of things that were available to it when we did those things. Maybe this one's a little newer here. I guess that I'm kind of beating a dead horse with these things. The objective for this is, yep, there's going to be a cost table. This one, a 9.6 down here, the 10 gig is going to be changing reference bandwidth to 10 gig. Yeah, that's right. It depends on what the reference bandwidth is. One square root model. What model are we going to use? We have the default costs, which are the ones that we saw in the other charts, and this is the chart I really needed. Fast Ethernet, the default is 1. We can change in the configuration the reference to these things, so that the Ethernet is now going to have the Ethernet, the 10 megabits per second is going to have a different cost than the 100 megabits per second, than the gigabit, than the 10 gigabit, so that it can do the calculations a little bit better for those when we look at them. Cost tables for these things to go from one to the other. The single area and multi-area, we've talked about those. The objective for CCNA, the 300-201 is a single area, configuring a single area OSPF, which there's not a whole lot of configuration differences between one or the other. If we have the multiple area, then we're just going to configure one area at a time. We'll configure this area, and then we'll configure this area. We have area 0 here. We're not really advertising anything. The only thing that we're doing here is having an interface, area 0 in our other area. These are going to be our ABRs, the area border routers, that take information from both areas and then can share that information back and forth across the areas to do that. The single area, all the routers are going to be contained in one area called the background area, and it's going to be area 0. We talked about that, and this is where I kind of get a conflict from the book that we have, and what Cisco's presenting is known as area 0, called the backbone area, the first area if we have a single area OSPF. And the other book says that, yeah, if you have more than one area, the first area, you need a backbone. You know, to avoid any conflict when you're creating these things, just create area 0 first. It doesn't really matter, it's just a number that you're putting in to do these things. Once that happens, and we have the multi-area here, every other area's got to touch area 0, the backbone area. So the multi-area hierarchical scheme, and the hierarchy is the areas, because the routers, the OSPF routers, only share information with the routers that are in the same area. And when you look at that, based on the things that we've talked about, subnetting and supernetting and those sorts of things, and the way that we did it at Roanoke, where we were all the 10.60s and somebody else was the 10.50. Hierarchical routing, or hierarchical assignment of the IP addresses can help you out a lot too, because if we do that, then we can send summary routes. Not as many routes have to go in the routing table. That means that when something comes in and is going from point A to point B, it doesn't have to, the router doesn't have to go through as many entries to find out where to send it. All the areas are connected to multi-area. All are connected to area 0. More commonly seen with numerous areas around area 0, you know, like a daisy or an aster, the picture over there. The connect to area 0 to another area is known as the area border router. We have those used in large networks, and I think that, if I call the right number, said about 50 routers was the maximum that you wanted in any area. To me, that's a lot of routers. This would be, when we talk about large networks, we're talking about really big networks. We're talking about a General Motors headquarters, an IBM headquarters, something like that. Maybe the Microsoft campus. Those kinds of things would be large networks that we could use this. Reduce the processing and the overhead. A failure in one area does not affect other areas if we have the multiple areas configured. The encapsulation of these things, it adds its own layer 3 header. after the IP header, and up at the top here we have the data link header, the IP packet header, and then the OSPF header, the OSPF packet type specific database. So it's going to add its own layer 3 header after the IP header, and let's see if we can see that Wireshark because we had that OSPF to do that. The IP header contains the OSPF multicast information. When we do that, let me bring this over here. This has got an awful lot of information on here, and again, when we do this, we can filter out OSPF. We have the multicast, we have the hello packets, the protocol here, OSPF. When we look at the IP header information, protocol, OSPF, and then we have the OSPF information that's contained in it. The header, version 2, it's a hello packet, the length, the source OSPF router, the area, this is in the backbone area, it's the only area that was in there when I was capturing these things. The hello packet, the mask 255 class C network, options for this thing, LLS data block present, and an external routing capable for these things, router priority. Designated router has not been elected yet, so we have all of the zeros. So the hello packets here to get the information going from them. Let's see, and it has a hello version, time to live, this thing, differentiated services, header version 2. Okay, the message type, and this is what I was looking for. Hello packet's a type 1 packet. And then we have a database descriptor. It's a message type. DB descriptor, it's going to be a type. Get that. A description. This is going to be sending some information down here. The extended TLVs for this thing. This is a link state database resynchronization. That's a description of these things. I'll have a little bit more verbiage. The request here is a link state type 3. The database description, type 2 here. The update is a 4. And an acknowledge is going to be a 5. So the different types of and what's in them, link state, announcement, LSA type 1, LSA type 1, LSA type 2, all of this is going on here in the acknowledge. I think that when we do that, we have the data link, the IP, the OSPF header, just kind of the process is going on. In the multi-access, the broadcast area, multicast addresses 224.0.0.5 and 224.0.0.6 conveniently for IPv6 FF02:5 and FF02:6. The packets, the hello, the database description, the 2, the link state request, the link state update, the link state acknowledgement 1 through 5. There are other link state announcement messages. If you do CCNP, you'll get into those. That's for the stubby areas, not so stubby areas, absolute stub areas, of different descriptors for different other network types. This particular time at this particular state, I guess, of the learning process, we're concerned with these summary for what goes on. The hello discovers the neighbors, the database description, checks for database synchronization between the routers. The 3, the request specific link state records from a router. I didn't get everything. Help me out here. And then the link state update is in response to a link state request. And then the acknowledgement, after we get the update, then we acknowledge everything that goes on. Just the different things that are going to happen within the configuration of the devices, or within the communication of our routers here. And in this thing, the hello packets used to discover neighbors, establish the adjacencies. We're going to advertise the parameters. Both of them got to must agree upon in order to become the neighbors, to elect a designated router and a backup designated router. The designated router, remember, is going to be the one with the highest router ID. If we configure the router ID, if it's not configured, well, first of all, we'll go back to highest priority, but typically we don't change that. We can, and the default's 1, and everything is set to 1. After that, the highest router ID, if that's not set, the highest loopback interface. If we don't have a loopback interface, the highest IP address on the router. The next one is going to be elected as the backup designated router, the BDR. And this only happens on multi-access networks. We have the routers connected to a switch, and we're going to say switch and not hub for these things. What they've said, the frame relay, not serial point-to-point links. Type 1, the hello. 2, database description, link state request, link state update, and then link state acknowledgement for these things. The hello interval, how often it sends the hello packets, and the router priority defaults 1, can be set from 0 to 255. If we never, ever wanted a router to become a designated router, or a backup designated router, we could set its priority to 0. The dead interval, how long it's going to wait to hear from a router before it determines that it's not playing in the game anymore. It's no longer active. The DR and the BDR contain the router ID for the DR and the BDR. And the list of neighbors is the router ID for the adjacent neighbor. Let's go back to this thing and see if we can see some of that maybe. When we look in this thing, the link state update packet, the link state ID, where this is where it's coming from, the advertising router for this thing, checksum, number of links, stub, and this is, you know, the data, the metric where we're going to, how we're getting there, sort of arrangement. And this is, you know, this is what the communication looks like between these things. The Internet Protocol here, IP protocol. We're back to the OSPF. Had maybe destination 224.0.0.5. The source here, OSPF version, the area ID. I think that these things, or at least I thought that it had. Yeah, the designated router had elected a designated router and a backup designated router. So we now know what the address is for those things. And then an active neighbor. All of that shared with these informations. The hello intervals for these things, hello and dead time, must be the same setting on the neighbors when we do those. And down a little bit, the setting is 10 seconds, every 10 seconds for the hello intervals for the multi-access, and every 30 seconds for the, so if we're using the serial interface every 30 seconds, we're using the fast Ethernet, gigabit Ethernet, or if we're back to Ethernet, they're every 10 seconds, and the dead interval is 4 times the hello interval. If it's on the non-broadcast multi-access, the point-to-point, then it's going to be 2 minutes, 120 seconds. If it's on the everything connected to a switch, it's going to be 40 seconds, which is quite a long time, really, in the networking world to wait for anything. So the dead interval is every 30 seconds, and then the transmitted to multicast 224.0.0.5 IPv4. I think we saw that in the packet itself, FF02::5 in IPv6. Convenient thing, both of them end in 5. And it's transmitted to the hello and dead interval, transmitted to the multicast address. This is what we're going to use to send the information to the DR, BDR. The DR and the BDR are both going to listen on that multicast address and take the updates. The BDR's got to keep everything up to date in case the DR fails. The link state updates, one or more link state announcements, contain the route information for the destination networks, and they initially send the type 2 database description packets, abbreviated list of the sending routers, and then type 3 link state request used to by the receiving router to request more information than the link state update. Going to send that in, and after we get the update, we're going to have the acknowledgement. And the one on the right over here, after we get 5, to do those autonomous systems, let's say router link state announcements, the types 1, 2, 3, and 4. And then we do have others that we're not really concerned with CCNA. You need to know that they exist, that they're there. Not so stubby area, external attributes, opaque link state. The process here, the state that we're going to go to get from one to the other, the down, no hello packets. Init, the initialization, the hello packets are received containing the sending router's router ID. Two-way communication is used to elect the DR and the BDR on the Ethernet link or fast Ethernet link. X start after that, and then we have the establishing the adjacencies. That's the first three states. After that, we're going to synchronize the databases. The X start negotiate the master-slave relationship in the database packet sequence exchange. The master initiates the DBD packet exchange, and this is just who's going to start it. The exchange, the routers exchange the database data, the database information. Additional information is required. Then the transition to the loading state, otherwise the transitions to the full state when we do these things. Loading, link state requests, link state updates used for the additional information, and then when we have full, the routers have converged. A process in order to get to the full state. Then we have our DR and a BDR, and then the druthers, the DR others for everything else that are not office holders. They didn't get elected. The adjacencies down to the init state. Hello, my router ID is there anyone else on this link that speaks my language? Multicast 224005. And then we go to 2 here, the init state. My router ID is, and here is my neighbor list. And this is going to be a unicast to 172.16.5.1, which is this guy over here, my router ID for these. And this is why router ID is why a unique router ID becomes absolutely critical. The neighbor list, R1 neighbor list, in gig 01, we get into two-way state. After that, R1, the default priority of 1. And the second highest router ID, it'll be the BDR on the link. And this is the election of the DR and the BDR based upon priority. And if the priority is the same, and it typically will be, then we're going to use the IP address as the highest IP address. Why have these things? And this goes back to the same thing that we looked at in a spanning tree when we looked at switches, connecting switches together. If we had a mesh network, and here we do have a mesh, everything's connected to everything else. How many updates are we going to have? If we have just a few here, 5 routers, 10 adjacencies, but we have 100 routers, we're going to have almost 5,000 adjacencies that go on. So the DR, the BDR is designed in order to reduce the amount of communication that goes on. Synchronizing, we got the establishment a little earlier, and then we're going to go into the X start. R2 has the highest router ID, so it will send a DBD packet before R1. And this is the master slave that was referred to in the earlier one. It's just which one's going to initiate the connection. So we get initiate. They're still going to exchange the information. And then step 2 here, the exchange state. Here's a summary of my link state database. Thanks for the information. Here's a summary of mine. So they start sharing the information, and then we get the acknowledgments that go back and forth. The loading state, I need more information. Here is the entry for about this particular network. Here's more information about it. And then the video, a few more slides here. When we get to the version 3, we're going to stop. I want to do version 2. Let's see how many slides we've got here. I guess I need to talk a little. The topology used to describe the OSPF configuration that we have. And these are the topologies that we talk about to the ISP. And then who are we going to talk to? Who are we not going to talk to? But everything in area 0. And we're going to have a common point of where we're going to go to get out. We're going to have a default gateway. Everybody's going to have a default gateway to get from one to the other. The router configuration, and these are things that I think we've looked at in some of the demo router OS, when we're configuring these things, router OSPF 10, we have to have the process ID. The process ID is a local number. It's a number that we assign so that the router can keep track of that particular OSPF process. And that's all it is. It is only significant locally. Other commands that we can have here, autocost, no, passive interface, priority. Router ID is set after we do the router, the command, and then the process ID for these things. We're in the configure router mode. Network is when we start, which networks are we going to advertise. And this is for version 4, because remember, for version 5 we configure it on the interfaces. The router ID, uniquely identify the routers, 32-bit number, and it's going to be, depending on what the configuration is, we can set the router ID with a router ID command. It's really high, the router will be collected as the designated router. Really low, then it's probably not going to be elected. 32-bit long, looks like an IPv4 address. Used in the election of the DR. If the priority is not configured and the priority default is 1, typically they're all going to be the same, unless obviously we go in and make a configuration change. The way it gets a router ID, with the router ID, if it's not configured, the highest loopback address, after that the highest IP address that is on for those things. The router ID command, show IP protocols. We're going to see some information, and these are all things that take a look at the configurations that you can do when you're playing with the labs. Try some commands out. Show IP protocols. What does it look like? What do I see with these things when I go from one to the other? The router ID, show IP protocols. And if we look in the list here, router ID is one of the things that's going to show up in the show IP protocols. Modifying the router ID, and we did this. We did the router ID command, clear IP OSPF processes. It's not going to change until we do this or we restart the router. So the router ID, applied the change once we do the reload, and the reload is at the privilege exec. Don't forget to make the router ID change effective, because it's not going to be changed until we restart the program. Loopback interface is the router ID. The older iOS versions didn't have the router ID configuration command. And so we could use, if we didn't want to change the IP addressing scheme on the interfaces, could use the loopback. And just interface LO0, it's a virtual interface that we can use on the devices. If we don't have a router ID, then the loopback interface is going to be the next thing that's going to be used in the election. Enabling the interfaces. We enable OSPF on the interface by specifying that network that the interface is attached to in the networks. And before it can communicate with other OSPF devices, we have to activate it on the other. So we would have to advertise this network here, 172, this network here, 172.16.3, on both of these devices. Once we do that, then these interfaces now speak OSPF. Until we do that, we're not going to establish the adjacencies for these things. So that's what this network statement here. And then we use the wildcard mask. Wildcard mask, again, if we do 255.255.5 and subtract the subnet mask 255.255.0, we get the wildcard mask. The wildcard mask is also the increment, whatever it is, -1. And then in the increment in the class C is 256, so 256 -1 gives us that. And also remember, the 256 minus the increment, just some math games you can play, equals the subnet mask. If you know, kind of things that you can check yourself with when you do these things, when we do these things. Does it make sense? The wildcard mask, the 0 checks to see if they match. The 1 ignores it. So, and the same thing here, the 255s minus the subnet mask. Either way, you can do this, but one of the checks on the wildcard mask is always going to be odd. It always will be odd. It's a series of zeros and the rest ones. The zeros 192.168, 2.0 network, 0 check to see if it's 192, 0 check to see if it's 168, 0 check to see if it's 2. The ones, it could be anything in that address range. The ones is what I say is the network command to advertise a particular network and advertise an IP address on the router. An individual, we talked about the host routes here. The host route, we would use a 0.0.0.0, checks all of them to give a route to an individual address. It says some find this easier to do the method 2 for this. Easier so the wildcard mask does not have to be calculated for these things. The wildcard mask 0.0.0.0 area 0 to do these things. You can do it either. And in EIGRP, we say that we're going to use wildcard mask there. You really don't have to put anything in it. We can make it so that it advertises everything, and what it would do is everything on the interface. Passive interface does not send OSPF messages, but will receive OSPF messages. Where would you want to do this? Maybe, the interface going to your ISP, so that you're not sending your route updates to your ISP. So passive interface, we're not going to configure it on the interface. You just use the passive interface command down here. Passive interface, gig 0, whatever, I said on the interface, in IPv6 on the interface. But in this one, we're in the show IP protocols. Routing is OSPF 10. Passive interfaces configured up here. Router OSPF 10, route passive interface, gig 00. So in the router configuration, we'll specify the passive interfaces there. The packet tracer, I have some if you want to do it, or you can create your own structure in packet tracer to build an infrastructure and to do the configurations. The cost metrics, I flailed around getting a table, but we have them here. This is an issue because it's the same cost from 100 meg to 10 gig. Not really exactly what we probably would want to be the case here. So this is an issue because it's the same cost and due to the default reference bandwidth, and it needs to be adjusted, and it can be adjusted for those things. So the accumulated cost is the destination network, the cost metric destination for these things. So we're going to use an accumulated cost to go from 1 for these things. And the next one is, we said that we cannot, the accumulated cost, and I don't think there's anything magic about that. The cost here is 64, and the cost here 1 is going to be a cost of 65 to get there. And here, over here we have the metric of. The other problem that we have is this one here. So you can change the reference bandwidth in this case and use the auto cost reference bandwidth command to change the reference bandwidth. The default reference is 100 megabits per second. We need to change it to something else. With the default, the 100 meg, the gig, and the 10 gig all have the same. What we're going to do down here, auto cost reference bandwidth 1000 command applied here, the 10,000 command applied. It's going to change this. So the auto cost reference bandwidth will change the cost of these things so that we now have different, more realistic costs for each of these things. The serial here 1.544, the 647 here, which was back earlier was the 64. The cost 647. 6477. We're basically, increasing the multiple so that we're going to have different costs for each of those. A configuration that can happen on these things will happen on these things. It costs here, let me see, show IP OSPF serial interface, and we'll see the costs. The previous slide, the commands to change the cost. The default interface bandwidth for those serial links default to 1.544. Show interfaces serial. We can change the cost. The serials 1.544 bandwidths are configurable that we can use for these things. These are all show commands. Show interfaces. Bandwidth 1.544. You can change the bandwidth with the bandwidth if you want to do those. So here we go. Adjusting the bandwidth. Bandwidth 64. And it is all of those that there's nothing really all that complex about any of these things. The changes are pretty simple. You just got to know where to go and what you can do. Adjust it at each end of the serial link because they got to match. And it's just a matter, again, going to the interface and doing the bandwidth command. But the bandwidth has to be configured at both ends. We can set the OSPF cost. No bandwidth 64 is used here to remove the command that was previously applied and reset the bandwidth back to the default, the 1.544. Over here we have the bandwidth command, the interface, bandwidth 1024, bandwidth on down the line. IP OSPF cost on the interface can be configured instead of verify the neighbors, show IP OSPF neighbors. We've done that a couple of times. We've looked at those. The neighbor ID, priority to state, the dead time, the amount of time remaining before it expects to receive a hello message, and then if you keep doing the show command, you can see those reset. The address of the neighbors, and then the interface. The protocols, and again, these are all things that once you're practicing doing the studying and you're doing the test questions or practice questions and you come up with these things, use the command, set up a lab to show yourself why it's that way. What works and what doesn't work with this thing. IP protocols, again, IP routing. NSF is the forwarding. It's using one of the forwarding. CEF, Cisco Express Forwarding, is the thing that you're going to see mostly. This would be maybe an older one, but we have the router ID, the number of areas in this router, one, normal 0, stub 0, not so stubby area, and again, things that normal is the ones that we're going to be, normal 0, or one normal, 0 stub and 0 not so stubby area. Different configurations that can go on. The normal are the only ones that we're really concerned about with. Verify, show IP OSPF, different commands to look at, and do the different commands. Look at, see what happens when you give these things. Verify the settings, show IP OSPF interface, and then show the IP OSPF interface brief. A little bit different look for each one of them. Here we have gig 01's got a DR here and a P2P point to point when we would configure these things. So different configurations available, and this is another Cisco lab. I have, and this is as far as we're going to go, this one.